Welcome to the second lesson. In this lesson, we shall explore the idea that are how to use the NetLogo system. The NetLogo is a computer environment devoted to simulations of several systems, in particular agent-based system. The program is open source and one can download it from the web, just looking for NetLogo from Northwestern University. There are a more developed version developed in Scala, essentially in Java, that works on computers, laptops, fixed PC, and so on, not on Android or iPhone devices, but there is also a version that is being actively developed on the web. And so if one develops a program, a model, it can be also distributed by web. There is a very large community using NetLogo, and so one can easily find helps, assistance, and so on. So let us investigate the system. The principle is that there is a world composed by patches, and so patches are essentially small robots, automata, that stay fixed on a certain point of the world, and on top of this world there can be moving agents that are called turtle, that can travel and so on. Turtle can be connected by links, and so one has a complete environment. So before playing with NetLogo, let's have a look live on the system, so that we can investigate the various elements. And so this is the world. We don't see anything, but actually it is composed by patches, so we can ask, give some command to a patch. Ask a patch, say 00, set your color white, so that we can see now the patch on the screen, on the world, and we can also inspect this patch and have a glimpse of properties. So what is the patch? The patch has a certain coordinates called the px core, py core. It has a certain color. If I change this variable, it can change color, and it has a certain label that can be shown in various colors, and clearly other properties can be added if needed. And okay, so the world itself can be examined. The world has an origin. In this case, it is in the center, but it can be in the corner, in the edge, and so on. And it has a certain dimension in terms of patches, and this is the patch size, and so one can arrange several things. Clearly, the world can be redimensioned, and this means that the size of the patches changes, not the number of patches. And we can also customize this interface by adding buttons with that invoke a certain command. Slider here, for instance, global variable, I don't know, a from 0 to 1, and then it can be moved. Then there are switches for Boolean values, and choose from with a different menu. Like this, and monitor input in order to get variables or numbers from the user, monitor that allow to look for a certain variable. Now we don't have any variable, but we can set it. For instance, we could choose the variable a, which is automatically defined by this, so that when I change this, I can see that actually it changes. And then we can have plot here that we shall examine in the following, and output, so areas in which one can print, and also notes for, say, my first model. So we have seen that we can address patches. Now I changed the coordinates, so the patches is in the corner, but I came back to the previous system, and I can also create turtle one, and then I can give it some command, for instance, set color red. Toothless. Okay, so I don't see much. Better to reduce the size, so the number of pages, so that it can be easier to see. So I can create a turtle. The default turtle shape is an arrow, but I can ask this turtle, turtle 0, and set shape no, circle. Circle. And but with the default shape is easier that to see that this turtle has also the heading, and can also be seen by inspecting this page, this turtle. This is turtle 0. One can see that it has a color like for patches, an ID that cannot be changed, and the heading. Heading is the orientation in degree. One have to remember that 0 is the north and 90 is east, so it goes clockwise, essentially the opposite of what is normally seen. It has also position. I can change this, and then this moves, a shape, a label, a color of the label. It can belong to different breeds, and one can change the dimension, and it has also a pen of a certain size, and if a pen is down, then when it moves, for instance, I can ask to turtle to go forward for a certain number of steps, and then to turn right of a certain number of steps, and then go right, and so on. And clearly, then turtle and patches can eventually interact with each other, and and so we can have a lot of different things. In order to have a glimpse of what is possible to do with this computer program, we may explore some of the models that can be found here, models library. But even before this, it is important to know that I can select a help from which I'm redirected to a web page in which one can find several helps and information. And so we can explore. Well, we can start from. Okay, first of all, we can explore some model library. For instance, a very simple one, which is directed percolation. Or just percolation. No? So here, then we shall examine what goes on. Here I have a classical bottling setup that prepares everything. Then I have a slider here that set the porosity of my medium. And in order to have a better look, let's say that we have a patch size, larger patch size with a smaller width, say 50 by 30. Okay. And then when they go, these are patches, and each of them can spread to different to neighboring ones with a certain probability. So if the porosity, if the probability is high, one has percolation. I means that the flux of water or liquid can go on. But if I reduce the percolation, and notice that I can do this dynamically, I interrupt the field. Clearly, it is better to study this for larger system, and so in this way one can have a better view of the problem. So with the 73% of porosity, the system percolates, and if I lower the porosity, then I reach a critical point in which it stops. So I can say that the threshold between percolating and non-percolating fluid is about I don't know, 64% or something like this. Okay. And so let us see what happens when I click on setup, on go, and so on. So I have to go into the code section, which is essentially an editor that allows to enter the code. The language is not so similar to other languages that can be encountered in computer languages. it resembles a bit Lisp. It is kind of a list-oriented computer language, but this is not very important. So, okay, let us see. So here I define some global variable. In particular, current row is the row that is active. This is the row where these red patches are, and this is also the fraction of the actual wet sites, so that I can plot the fraction during time, how, for instance, it decreases when for instance, the fraction of wet soil goes to 0. This is the total amount, so it is the cumulative of the fraction. And okay, so actually this is the code that is executed when I click on setup, this button here, and almost always one starts with clear all, which simply cleans up everything, setting the total amount of oil of liquid to 0, and this is a command to patches that actually is defined below, and to reset color, and essentially they say if they are in the odd or even side, they are brown or a kind of gray, so that to have this checkboard pattern. And okay, now they reset the current row to the top one. The top one is the value, corresponds to the value of maximum coordinates, max py core. And now they read only those that are on a certain number, certain coordinates. And this is also a command that is usually encountered in setup. It resets the clock of the system. This is this counter here, because for each clock the system updates the plots and also the display, and so this is a way of resetting. Bene, and this is the other, what is executed when I click on the go button here. And the go button, very simple, it says, okay, if there is no patches in the current row that are red, the execution is stopped. In fact, you can see that this go has this strange icon here, because it is a button that goes forever. It is like if one was continuously clicking on this button until something happens, until I stop it, or until the execution is stopped by the program itself. Otherwise, it asks to percolate, go on one step, and to wrap when it arrives at the end of the word. And so percolate. So let's have first of all a look at the language. You see that it goes on selecting sets, for instance, those that have that belongs to a given agent set. It is a set of agents. and that are those patches with pi y core equal to max pi core at the beginning, and then we shall see what are they. And so essentially these are the ensemble of patches on the current row. These are selected, I selected those that have color equal to red, and this is a test on this set that gives 0 if it is false if it is empty, and true if it is not empty. And clearly this is the reverse. So I execute this only if in the current row there are no patches with p color equal to red. Otherwise, I call percolate. Here it is the subroutine. And percolate asks to the patches belonging to the current row, which have a color equal to red, to ask to patches that are with respect to them at the points -1, -1, and 1, -1. I mean that if this is the current row, and this is one of the patches with color equal to red, then it tries to communicate to these two other patches that since this is the y direction and this is the x direction, they have with respect to that coordinates -1, -1, and 1, -1. And so these are the two patches here. This is essentially a list of lists in NetLogo language. And so the first list is this one, the second list is this one, and this is the list of lists. And notice that lists are not separated by commas, but just by spaces. Actually, another thing that we can notice is that variables can have almost any character in the name. This means that if I want to perform computations, arithmetic computation, I have to separate operators by space, because if I stick the plus to this is simply another possible name for a variable, which is not what I want. Okay, so we ask at these two patches what this is what we ask, and say that if they are brown and with a certain probability, random float gives a random number between 0 and the number here, and this is confronted with the porosity, which is the variable defined in this slider, and goes from 0 to 99%. And so I ask them if these conditions are met to become red. And then the ones becomes black. We are still inside this loop. And I set the total number of oil plus 1. Now I add to the current row the patch at 0, -1 of current row, and notice that this is a manipulation of an agent set, but in NetLogo I don't really change variables. What I do is I take a variable, for instance this current set, I manipulate it, and then I assign it to another variable which can have the same name of the new one, but actually variables are not mutable. And finally, there is this final procedure to, if they arrive to the end, they are moved to the beginning of the row in order to start another iteration. And so this is an example, not a very complex one, although there are some interesting points. And okay, just to have an idea with turtles, then we shall develop another one. We can, for instance, have a look at an example that we shall study in the following, which is a Monte Carlo simulation of particles interacting through a Lennard-Jones potential. That is a potential which has a minimum at certain distance. We shall investigate in detail this in a few lessons. And so the idea is that we can load this from the library. Here it is. And so one can recognize several of the elements that we have examined. These are labels, notes, that here can be changed, but and in this arrangement I can set up the number of atoms, the density corresponding, and clearly the initial configuration, if they are arranged in this hexagonal lattice, which corresponds actually to the minimum of the energy, or at random. This is a chooser. And then I can set the temperature, and then I can watch the system go once or go forever. And so clearly, for the moment, we are not interested in the actual dynamics, but actually you can see that these two buttons execute the same procedure. So, but the only difference is that one has this forever box checked, so that stays pressed, while the other not. And the code now is much more complex, but what is important is that each of these balls are actually turtle, and so one can see that these turtle have a certain ID, again a certain color, which can be altered, a certain heading which is not really used here, coordinates, shape, label, size, and also other properties if needed. And so this is Tarto 219, and so they move. I can also, for instance, ask Turtle 219 pen down, so that now I can trace all moves that this particle tries to do. Clearly, some of them are not accepted because it is this Monte Carlo simulation, but clearly, if I increase temperature, much more of them are accepted, and so the particle can really move away from where it is. And okay, this is the Go section. So for each of atoms, because so a Monte Carlo step, as we shall see in the future, is composed by a certain number of elementary move, one for each component of the system. So in this case, they are this number of atoms, and so for this number of components, we ask one of them at random to try to move, and it can be accepted or not. And there is also an adaptation section in which the, the movement of the trial is adjusted so that to have a right, so an acceptable acceptance rate. And so this is the fraction of the attempt to move, and then clearly there are a lot of other different pieces of simulation. But we shall examine this code in a future lesson. But for the moment, let's have a look at another model, which is the one in which we shall see the presence of both turtles and lynx. So this is a giant components, which is an example that we shall meet near the end about networks. So in this case, the problem is very simple. Choose two people at random in this community and link them. And here it is computed the size, so the number of people belonging to the cluster which has the higher number of components. So we can go again, and this is in some sense something that resembles the birth of the internet, because internet started with a few laboratories of universities that started to connect each other to exchange some data. But what happens is that at a certain point, networks get connected, and so you can monitor here the size of the largest component of this graph. And what happens is that at a certain point, this component becomes, say, quickly macroscopic. I mean, most of people are connected. So essentially, this is the birth of a giant component, or in this case of internet. Clearly, still a lot of leaves are left alone. A lot of people are not connected, or there are still unconnected subnetwork that quickly become part of the giant component. And clearly, this is best appreciated when one have a lot of different people. Clearly, we can go faster by essentially refreshing the layout less times, and so one can watch at what happens during time, and you can see that actually there is a sudden increase of this giant component in time. And you can also notice that NetLogo is essentially a slow system to perform simulation, even though there is a possibility of going faster using some feature. Just to have an idea of interaction between turtles and the patches, we can go to the rabbit grass. So this is a kind of competition model. In this model, we have rabbits that eat grass and reproduces, and there is a certain threshold for which a rabbit that has accumulated a certain number of energy can reproduce. Rabbits are turtles that move at random, while grass is represented by patches, so they can accumulate energy by the sun with a certain rates. So and there are also weeds that are bad grass, and okay, so they can interact, and according to the number of components and to this threshold, one can have the equilibrium at a certain point. Clearly, if I increase too much the reproduction rate of rabbits, I tend to destabilize the system because they start to reproduce widely. You can notice that they also form aggregates, a feature not well captured by mean field models. And clearly, if now the growth rate of grass or is too little, also rabbits tend to suffer. Clearly, if I also introduce weeds that give no energy, also the rabbit population goes to 0. And okay, so this is a classical model to play and to compare the results. For instance, here we have extinction of rabbits. To compare results with respect, for instance, models studied by means of partial differential equations and so on. And okay, so let us also see other possibilities that can be quite useful. In particular, there is a possibility of clearly editing shape of turtles, so that one can customize the display as what wish of links. But the one interesting thing is this behavioral space, which is essentially a way of performing experiments, for instance, experiment with this model, by changing some of these parameters, or more than one, running a certain number of experiments without a display, so in a relatively fast way, measure something, and have the results reported in a spreadsheet. So this is an interesting opportunity. And also the simulation is performed in parallel on all the cores of the computer. So if one has a computer with several cores, can program quickly the field. But another interesting point is that actually there are also a 3D version of NetLogo, and so that even with some limitation, one can also develop and run three-dimensional models that we shall meet in one of the following lessons. And when it decides to start, we shall examine it. Not really willing to work. But okay. We shall come back to 3D logo. Okay, it is slowly starting, and waiting for the 3D version, I mentioned that there is also the possibility of having more clients running together. This can be useful if one essentially wants to let people participate, like in a shared game. Okay, the 3D version has started. Let me see if I can show it. And so this is the 3D version with its command space, with the code and so on. And for instance, we can have a look at some model. Let me see. In physics, some kicked rotator or Leonard Jones. But these are two-dimensional. Say this neighborhood example, so that you see that it is a real three-dimensional systems in which patches, or in this case turtles, can change form, shape, color, and so on. And we shall see an example in the following. Okay, so let's start with a very simple model from Scratch, so that we can appreciate. The idea is to have a system that simply paints at random a certain number of cells. And so what we need is just a button for the go, a slider with a certain probability. From, say, since we are physicists, I prefer to use the standard definition of probability. And we can also add a monitor just to check what is produced is what I wanted. And so this is just, say, the count patches with the color equal to red, and then I divide it by the size of the world, which is world width times world height. 3 decimal places are sufficient, and maybe I can change the display real probability, so that it is reasonable size. Okay, so up to now we don't have anything here. So we go to the code section, and to go, I set clearly at the beginning clear all, and then ask patches with the certain probability. So I draw a random number. Random float 1 is a random number from 0 to 1. So if this random number is less than probability, then I do something, and that's all. And what I do, I just ask, and I just say set peak color red. So when I go, I have a certain number of patches with a certain color. As you said, I put here the code of the so-called reporter, but I could have put this also, say, compute fraction. I can insert here the code instead of directly inside the button. And this is in NetLogo language called a reporter. So essentially, these are procedures that do not report, do not return anything. These are functions that report something, but the syntax is essentially the same. The fact is that I have to report what is the result of computation, and there is a primitive called okay, I have to then give the name compute fraction, and okay, so when I go now here, I take the result of the reporter. So essentially, it's up to the choice to concentrate all the code into the code section, or split it into the, say, the main core and the reporters, and so on. And then finally, there is an info section that can be edited. And here, this is the first example in NetLogo. One can produce some documentation, and here are just hints because this can be edited. And in this way, I can produce several things. Okay, so we can summarize what we have learned. That we have learned about random number generators, conditional expressions, that the names can contain any character. The color is a patch property, and sliders define global variables. I don't have to redeclare the variable inside the main code. And that the monitor contains procedures that are also possible inserted into the main code. And if I want to define a local variable, I can give them the value with let. And notice that again, the equal is the test for the quality and not the assignment. Assignment is done with let and set. Set assign a value to a variable, to a global variable, or a variable that is already defined with let. And then essentially the whole philosophy of NetLogo is based on working with list, ordered list or unordered list called agent sets, and which can be manipulated. And sliders are actually simple things. And okay, let's go to a second example, this time with turtles. And I want to define the game of life, which is a famous game invented in the 70s by the Conway, who was the mathematician who invented this game, died just months ago. And okay, so this is a way of playing with an artificial environment, which is called artificial world in some sense. And so in this world, we have two states, and they are alive or dead. And the rule of evolution is that a live cell remains alive if it is surrounded by 2 or 3 alive neighbors. A dead cell becomes alive only if it is surrounded by 3 live neighbors. And otherwise, the cell dies. And it is interesting because we can do with several there are several mathematical problems that can be addressed with the game of life. And it can be programmed using patches or using turtles. Let's start with patches. So we just need to have a button for the setup, just to generate all the patches with a certain probability. And we can have a slide. We can have a go button, a step button, which is essentially the same, and a fraction of red patches. Okay, so since the game of life has to be run in parallel, while the updating here is essentially serial in a random order, we have first to save the number of live neighbors in some variables for all patches, and then to do something with these patches. Okay, so let's go to the code. So we start assigning a button for the setup, a slider for the initial probability, say from 1 to 0 to 1 in some fraction. And then we can add the step button. Actually, the step is just a name for a go. And the real go button, which runs forever. And then we can have a monitor, okay, as before, a fraction of alive patches, and this is the name. And here we can count patches with color equal to red. Divided by world width times world 8. Something wrong, patches So let's go to the code so say patches own number of alive neighbors, which is a variable for each patch. Then to set up clear all, ask patches if random float one less the initial probability, set the color red. That's all essentially, and I think that is enough. Clearly. And then to go, I first ask patch to compute the number of alive neighbors. Ask patches set number of alive neighbors, count neighbors. Neighbors is a pre-configured agent set that contains all the agents in the 9 and in the 8 neighboring cell. So I refine this saying that I want them with the color equal to red. And then I again ask patches, and then I have to say that now I can program this in several different ways. For instance, the simplest way is if they are surrounded by 3 alive neighbors, if number of neighbors equal to 3, or the numbers is equal to 2, and the color equal to red, they set the color red. But in the opposite case, I have to set the color black. So I have to use if else, which includes also the possibility of doing another things. And this is enough. But if I want the tick to increase here in the interface, I have here to reset ticks and here to tick. Notice that if I press tab, they are the syntax is displayed. And so let's check. Then okay, so clearly I can watch the game step by step or let it go on. Here I have the fraction of alive patches, and now I can say increase a lot the dimension of my system in order to have a look at this live game. And watching this, one can imagine why it has been called live, because actually there is a movement like in a colony of bacteria, so on. You can see also that there are animals that travel inside the system, like this one. They are called the gliders. Other oscillating things, other fixed, called still life. And And clearly the system is interesting. What is surprising is that this has been studied a lot before computers became available to everybody. So essentially playing this with, say, fish, coins, or something like this on a real board. And okay, so we can also um, change a bit uh, the rule if we want and examine what happens in other cases. But if better is to explore, to build another different problem, the last one, maybe in 2 or 3 dimensions, which is based on turtles. So let uh, let's say this as life, and then from scratch we can try to model another interesting model, which is the diffusion limited aggregation. I mean, in which chemical particles wander at randoms, and if they met a seed, they stick, and so they form a kind of fractal, growing fractal. So again, we need very few elements, just a button here to set up, a slide, say, to set number of particles, and in this case it is a number, so we can go, say, up to some thousand particles, and then we need the go button. Okay, there we are ready. So let's go to the code section. To set up, we can simply generate a clear role. We can create turtles, the number of particles that we need, and they ask them to set the color red, set size, set a number in terms of patches in order to have them more evident, set shape circle, say, set xy random x core, random y core. All of these quantity here are defined in the helper, so I can check this. But clearly, at the beginning, one has to have a look at the various commands, or better, to study one of these several guides that are included into the programming language. Okay, so I think that that's enough, and then we have to set the seed. So I ask fetch at 0, 0 to set p color green. Okay, so let's check create turtles. No, patch at is the patch which is at a certain distance from a turtle. So I need check two patches simply. So clearly these are the better if I increase the number of my word. Okay, so these are 3,000 particles scattered into this word, otherwise I can diminish the number of particles. Okay, so we now are ready for the go procedure. To go, I ask all patches to turn their heading at random, go forward for a certain amount, and if they are within a certain radius of a patch to which is green, they ask the patch below them to become green and then die, so disappear. So to go, ask turtles right 360 degrees, so right, left, so this is essentially right random 360, so they turn at random, and they go forward by one step in the direction of the heading, and then I have to check if there is at least some of the neighbors green. If any neighbors with the color equal to green, so this is, you have to notice that the turtles can access the variables of the patches below them, and for this reason turtles have a color and patches have p color in order to have different variables. So if any neighbors with p color equal to green, they can manipulate the color of the patches below them and then die. And clearly I can add here reset ticks and then tick. Okay, this is finish the procedure, tick, and okay, so this should be the code. Let's see, we can start. So this should be the code. Let's see, and we can see that the fractal is growing. The plot monitors how much is his mass, and you can notice that there is say a region near this fractal where the density is lower. Actually, particularly I have difficulties in entering the internal part of this fractal. Actually, this is not a real fractal, as we shall see when we shall investigate the self-organizing criticality. This is a fractal only in the limit in which only one particle at time is arriving. And so now what we could also add is a way of having the simulation stop when, for instance, one of these green patches is birthed around so at the boundaries. So we can modify the code. If px core equal to max px core or px core equal to min px core or y core and py core, which are the coordinates of the patches, equal to min py core or py core equal to max py core, I have to stop the simulation. The problem is that I cannot use a stop here because a stop stops the most inner loop, which is essentially this one. So it's better if I define a variable as false. I set here true, set stop true, and then here if stop, now it works, I hope. And this is an unfortunate situation, but this is like this. But you can notice that I can resume the simulation from where I stopped, even though I changed the code, because the world remembers the position of turtles, and they retain their values, colors, and so on. And okay, let's see if it really stops when arrives near the border. Okay, maybe this one. Or in this case, okay, they stopped actually, and so this works. Notice that the coordinates of the world are periodic, so that I can set up simulation with very small number of particles. I can also ask some of them to leave some track. And if I'm lucky, I could see it to go in wrapping around the world. I don't know if this will happen or not. It may also happen that this particle will stick here. So this is an example of a random walk, what we shall study in one of the next lessons. Yes, you can notice that this particle crossed the world, and so in this case we are using periodic boundary condition. If we like to use a fixed boundary condition, we have to check if the particle tries to go out the world or not, in order not to have an error message. And maybe if we are lucky, we can now okay, see the particle that stick to the growing crystal. So we can also save this as an example to be uploaded to our examples. And I think that we are done for this lesson, and we shall make use of NetLogo in the future in the whole course. Clearly, for the most simple example due to the limitation of the program. Bye bye.